Okay, so in this second numerical example, which is example 15.9, and this example is taken from the RC Hibbeler book, and again, it's one of the numerical example in your tutorial sheet. So as you can see that the bag A, which is this bag here, having a mass of 3 kilogram, is released from rest at the position theta equals 0. So when theta is 0, so this means that the bag A is in this position here. After falling to theta equal 90, so when this bag will come to this position here, it strike a 9 kilogram box B, which is this box here. If the coefficient of restitution between the bag and the box is 9, e equal zero point 0.5, determine the velocities of bag and box just after impact, and what is the loss of energy during the collision. So in this example, what you are given, so if you consider this this diagram here, so you are given uh, the MA, which is 3 kilogram, MB is given, which is 9 kilogram, and a 3 kilogram is released from rest. So this means that the uh, if you consider this figure here, so this the if we consider this is position 0, so this means that velocity 0 is 0 here, meter per second. So it is released from 0 here, and then it will come to this position here. So we will call this position 1, for example. So and this angle here is then 90 degrees. Okay, and in this case, then it will strike this box here, which is box B, and this is particle A here. Okay, so in this case, what you need to calculate, so requirement is, so after impact you need to calculate the velocity of A. So you can call it VA dash, and you need to calculate VB dash, which is the velocity of A and B after impact. And the velocity of A is again at this location. We know that the velocity of A will be in this direction here, and B is uh, so this will be VA, and VB is 0, because this box is stationary here. So VB is 0, and we need to calculate VA, because the this bag is coming from here to here. So it should have some velocity here. So you need to calculate that velocity also. But in addition to this, then after impact, we have to calculate VA dash and VB dash. So this is our part A. And in part B, then we need to calculate loss in energy, or which is loss of energy during impact. Okay, so if we start with the part A, so the first thing that we need to do is to calculate VA. So VA is the velocity of particle A just before impact. That is, the body is moved from this position 0 to position 1 here, which is the position of particle A just before impact. So to solve this problem, that is to calculate VA, you can either use the basic equation of, of motion, or you can just apply the work and energy equation, which is, I believe, is straightforward to apply. So if we use um, work and energy equation, so work and energy equation is that we are applying this between these 2 points. So work and energy equation between position 0 and 1. So if we apply this work and energy equation, so you will have the initial kinetic energy, which is T naught, plus initial potential energy, which is V naught, and plus work done between position 1 and 2, and this is dash, and then you have T1 and plus T2, sorry, V2. So T naught is the initial kinetic energy at location 0 here. V naught is the potential energy at location 0 here, which can either be elastic potential energy or gravitational potential energy. And then the work done by any force between this point and this point, other than gravity and and elastic forces. And then finally, we have the final kinetic energy at location 1 and potential energy at location in location 1 also. And in addition to this, you are also given this distance here. So this distance from here to here is 1 meter. So this means that this if this distance is 1 meter, so this is automatically 1 meter because this is just the radius of this circle here. This is also 1 meter here. Okay. So now if you take this as your h is equal to 0 position here, then we can apply this principle here. Now, if the kinetic energy, if the velocity is 0 here, so the kinetic energy is 0. So this means that this term will equal to 0. Similarly, the potential energy, in this case, there is no spring, so there will be no energy of the, there will be no elastic potential energy. The only potential energy here is the gravitational potential energy, which is mgh. So what you will write is mgh and h naught. So we will call this as h naught here. Okay, and then you have the work done. So in this case, there is no other force other than gravity and and elastic. So there is no other force here. So this work done is also 0. Now finally, in this location here, in location 1, what do you have is you have the kinetic energy, which is obviously the body is now have some velocity. So va is not 0, so you will have half mva square, and plus this term is 0 because here h is 0, so mgh will be 0 here. So in this case, now from this equation we can calculate va. So obviously you can cancel m with m, so va become equal to 2gh. So in this case, if you say 2 times 9.81 into h naught, which is 1 in this case, so from here you will get the value of this va, which will be 4.429 meter per second. So we managed to calculate this va, which is the velocity of a just before impact. So now if you look at this this impact here, so it is again just a central impact because the uh, body B is not moving. The only body which is moving is A. And if you join the center of gravities of these two bodies, so the velocities are in the direction of the line of impact, and therefore it's just a central impact here. So again, we will be able to apply the procedure for the central impact to calculate the velocities after impact, which is VA dash and VB dash. You are given VA, VB, their masses, and you are also given the VB, which is 0 in this case. So now, if we use the law of conservation of linear momentum, Okay, so if you use the conservation of linear momentum for these two bodies, so one is A and one is B, we can write that MA VA plus MB VB equal to MA VA dash and plus MB VB dash. And obviously this law can be applied to the whole system, to the two bodies here. You cannot apply this to individual body, so you have to apply this to the system. Okay, so now the VB is 0 here, so this means that this term will be 0. So this means that this term is 0 here. Now we can put the values of the remaining known quantities here. So okay, so we can put the values here. So MA is known, which is 3 here. And VA is known, which we just found out in the previous case, so which is 4.429. And on the right hand side we have MA, which is again 3, and VA dash, which is unknown, and plus MB. So MB in this case is 9, and you are also need to calculate VB dash. So now we can simplify this equation here. So if you simplify this equation here, so what you will get VA so VA dash will be equal to 4.429 and plus 3 you get this equation here. So this is this is our first equation that we get here. And now in this equation, as you can see that there are equation, you can call it equation A. So now in this equation there are two unknown, VA dash and VB dash, and this is just one equation. So now we need one more equation, and which we will get from the coefficient of restitution, so which is E in this case. And as you know that E is given, which is 0.5, and E is the just the relative velocity of separation, and divided by the relative velocity of approach. So in this case, we will write this VB dash minus VA dash divided by VA minus VB. So if you just put the limits, put the values here, so what you will get VB dash minus VA dash and divided by 4.429 minus 0, because this velocity is 0, and VA that we have here is 4.429. So now again we can simplify this equation, and what we will get is VA dash is equal to VB dash minus 2.145. So this is our equation B here. Now we have two equations now and two unknown, so we can solve these equations together and we can calculate VA and VB. So here VA will be equal to, so VB dash become equal to 1.661 meter per second, and VA dash become equal to minus 0.554 meter per second. So we managed to calculate VB dash and VA dash from these two equations. So this was our part A of the problem. Now in part B, we need to calculate the loss of energy. So to calculate part B here, so we will calculate two energies. So E1 is the energy just before impact, energy just before impact, and this energy will be equal to half ma va square plus half ma mb vb square, and then you have E2, which is energy just after impact. Okay, so in this case, it will be half ma uh, v a dash square and plus half mb vb dash square. You have these two equations. This is the and in this case now we know the velocities and we know the masses, so we can calculate E1 and E2. So the loss in energy, which you can say is delta E, will be just equal to the energy before impact minus the energy after impact. So E1 minus E2, and obviously the energy before impact will be greater than the energy after impact. So from here you will get 16.6 joule.